In the vast silent theater of the cosmos, not all stars are gentle beacons of light, some are cosmic predators. Have you ever wondered why, in our search for life, we find so many barren, scorched worlds? Why do 90% of planets near certain stars get fried? Because some stars don't just burn, they just shred. They don't just warm their planets, they violently tear them apart, atom by atom. They are the universe's most extreme, most violent, and most terrifying objects. Let me show you the worst offender. There's a class of star called a magnetar. The name itself sounds like something forged in a cosmic nightmare, and the reality is far more extreme. To understand this monster, we have to witness the death of a giant. Imagine a star at least 20 times more massive than our sun. For millions of years, it burns through its fuel, a colossal furnace of nuclear fusion. But when that fuel runs out, gravity, the relentless architect of the cosmos, wins. The star's core collapses in on itself in a fraction of a second, triggering a supernova, an explosion so bright it can outshine its entire galaxy. While the outer layers are blasted into space, the core is crushed into an object of unimaginable density. A neutron star is born. This isn't a star in the traditional sense, it's a city-sized atomic nucleus. A single teaspoon of its material would weigh billions of tons on Earth. But a magnetar isn't just any neutron star, it's a neutron star, on steroids. During its violent birth, if the star is spinning fast enough, a process called a dynamo effect kicks in. The star's magnetic field is amplified to an insane degree. This is the genesis of the magnetar. And its defining feature is a magnetic field of incomprehensible power. It packs a magnetic field 1 trillion times stronger than Earth's, 1,000 times stronger than a regular neutron star. Let's try to put that into perspective. The strongest magnet ever created by humans is millions of times weaker. If you were to bring a magnetar within 1,000 kilometers of Earth, it would wipe the data from every credit card on the planet. Get too close, say, within the orbit of the moon, and it rips atoms apart. The magnetic forces would stretch and squeeze your body until you were reduced to a stream of fundamental particles. This isn't science fiction. This is physics at its most brutal. The magnetar's crust, a solid lattice of iron nuclei, is under constant, unimaginable stress from the magnetic field twisting beneath it. Eventually, it breaks. These are called starquakes. They are trillions of times more powerful than the strongest earthquake in Earth's history. When the crust cracks, the tangled magnetic field lines beneath are unleashed. They snap and reconfigure themselves into a more stable state in a process called magnetic reconnection. This event releases a colossal amount of energy in an instant, in the form of X-rays and gamma rays. This is a magnetar flare. The physics here are so extreme they break the rules of our everyday reality. The magnetic field is so strong that it affects the vacuum of space itself. According to quantum electrodynamics, empty space is filled with fleeting, virtual particles. A magnetar's field is powerful enough to warp this quantum foam, an effect called vacuum birefringence. It means the empty space around a magnetar behaves like a prism, splitting light that passes through it. The void itself is altered by this star's presence. This isn't just theory. We've seen what these monsters can do. On December 27, 2004, a giant flare erupted from a magnetar named SGR 180620. This magnetar is 50,000 light-years away, on the other side of our Milky Way galaxy. Yet, the burst of gamma rays was so powerful that when it reached Earth, it slammed into our upper atmosphere, measurably disturbing the ionosphere. Satellites were blinded. For a few terrifying moments, a star halfway across the galaxy had a direct, physical impact on our planet. In just 1/10 of a second, that flare released more energy than our sun has produced in 100,000 years. And that was from 50,000 light-years away. Now, imagine one of these much, much closer. The threats are threefold. First, the electromagnetic pulse. It fries electronics from light-years away. A nearby magnetar flare could instantly disable every satellite, every power grid, every computer on Earth, plunging us into a technological dark age. Second, the radiation. It can blast gamma-ray bursts that scramble planets. A direct hit from a giant flare within a few dozen light-years would be an extinction-level event. The gamma rays would obliterate our ozone layer, exposing the surface to lethal solar radiation and triggering catastrophic climate change. One flare could fry atmospheres across whole solar systems. Any planet, unlucky enough to be in the direct path, would have its atmosphere stripped away, its oceans boiled off, its surface sterilized. It would become a dead rock in a matter of hours. So, should we be worried? The good news is that magnetars are incredibly rare. Astronomers estimate there are only about 1 billion neutron stars in our galaxy, and only a fraction of those become magnetars. We've confirmed about 30 so far, and none are close enough to pose a direct threat. The closest known magnetar is thousands of light years away, but the universe is a very big, very old place. The question isn't if a magnetar could threaten a civilization, but where it has already happened. Finding these cosmic phantoms is a challenge. They are tiny and often shrouded in the dust and gas of the galactic plane. We can't see them with conventional telescopes. Instead, we hunt for their violent signatures. High-energy space telescopes, like NASA's Chandra X-ray Observatory and the Fermi Gamma Ray Space Telescope, are our eyes. They scan the skies for the telltale bursts of X-rays and gamma rays that signal a magnetar's tantrum. Sometimes, we also detect them through radio waves. In 2020, for the first time, astronomers traced a mysterious, powerful signal known as a fast radio burst, or FRB, back to its source, a magnetar within our own galaxy. It confirmed that at least some of these enigmatic cosmic radio flashes are powered by magnetars, solving one of modern astronomy's biggest puzzles. So when astronomers point their instruments at a magnetar, they do so with a mix of excitement and profound respect. Each burst of energy, each flicker of data, is a message from the most extreme physical laboratory in the universe. They whisper, danger. They teach us about the fundamental forces of nature, about the life and death of stars, and about the raw power simmering just beneath the calm facade of the night sky. They are a reminder that the universe is not designed for us. It is wild, chaotic, and magnificent in its violence. Cute to look at from a safe distance, deadly to everything nearby. That's the universe's ultimate fire hazard.